All right, folks, I'm going to get started on the talk here. So I'm going to present a little bit of an unusual talk, not necessarily strictly related pertaining to security as a profession or an industry, but instead kernel hacker stuff that may or may not be relevant to all sorts of security applications and sort of an underappreciated or at least underknown kernel facility that will hopefully be growing in the next few years. So seccomp is short for Secure Computing Kernel Facility. It's been around for a little while and is really only recently coming into vogue. But it basically is a way for a process, a non-privileged, non-root process, to voluntarily make a one-way transition into a mode that now has a limited amount of access to the kernel's APIs. So it's a way for a process to forego a lot of its kernel access and a lot of things that it can potentially do with the kernel. There is a big disclaimer on the seccomp kernel documentation that says that seccomp itself is not a sandbox. It's not a security feature. It is used to implement security features in defense in depth, but critically it's not and never claims to be something that you just turn seccomp on and you get security. It's not that simple, and part of that is why it hasn't seen a lot of widespread adoption like AppArmor or SE Linux, as much as we can say SE Linux has seen wide adoption. So, before digging into seccomp specifically and how it operates, I'm really going to go from sort of a ground-up basics of what syscalls are and why you might need to care about them in a security context. So, on modern code, and modern code meaning everything that's not a TRS-80, processes, or you're running many processes on a computer, these processes are isolated from each other, and a process as it runs is really only seeing a very abstract representation of the machine that's presented by the ISA. And it's also important to understand that when discussing this sort of very low-level process architecture thing, privilege level is a very distinct concept from what you might think of like a Unix user privilege to a processor, to an ISA. A process that's running at root is still absolutely the lowest privilege level because it's still a process. It's user code, even if it is root, it's just an entirely different concept. But the critical thing is that as long as a process is running, it's only really seeing this abstract machine. It sees its own memory space, it sees its own instructions, obviously, and executes happily, blissfully unaware of everything else. And any interaction it wants to do with the outside world has to go through the kernel. That's what the kernel provides. Oftentimes you'll see this abstracted into the kernel provides a hardware abstraction layer, which is a bit of an oversimplification. Yes, it provides I/O facilities, but also everything that the process might do that might care about other processes, whether that's spawning additional processes, all forms of IPC, all of these have to be provided by the kernel through some form of kernel API. And those kernel APIs on Linux, on Windows, except for weird obscure things, on Mac OS, on Darwin, and even in embedded systems, sort of RTOSes that you're seeing, you still will pretty much always see this sort of concept of a system call. And that's a particular instruction or technique provided by the ISA itself that somehow allows the processor to transition from that low privilege level user mode, process mode, up to machine mode or supervisor. There's all sorts of different languages or different terms for it depending on the ISA. And there's just a couple of examples up there. Int 80 hex is the 32-bit, x86 syscall is 64-bit. If anyone knows what TOX6D syscall instruction is, I'd be pretty proud. But anyway, so the syscall instruction is arguably the most important instruction in an ISA when it comes to how communication, how privilege levels escalate to something that can now communicate with kernel space. When a process that's running in low privileged user mode executes a syscall instruction, the processor and hardware vaguely performs this sequence of events. The particulars are very dependent on the ISA and typically described over a page or more of text. but it will save as much as it needs to know about the execution state to be able to restore this process to exactly the way it is at some point in the future. It'll change its memory mapping into a kernel mode memory map. So now instead of the processor as it executes seeing sort of that process's memory image, it'll see something different to something more, seeing into IO space, etc. It'll increase to the new privilege level, and then it'll just start executing instructions somewhere that's been configured at an entry point handler of some sort in the kernel or supervisor software or whatever sort of kernel design the operating system in question is using. And then it enters, and at this point the kernel can begin executing code and figure out what is the process requesting that I do on its behalf. So you can think of a syscall as a function call, just with maybe a few extra steps. A process can execute a syscall by basically setting up any sort of buffers it needs. You know, if it might be requesting the kernel to give it some data, it might need to set up a buffer to receive that. So similarly, if it's trying to provide some data to the kernel to do I/O with, it will need to populate that data into a buffer to prepare to give it to the kernel. And then it'll be placing arguments like pointers, flags, telling it what to do, sizes, lengths of things, set those all up. Typically on modern OSs, these are all just placed in a couple of specific registers, just like a function call. And then it executes this syscall instruction where it traps up into machine mode and the kernel takes over, begins executing code, knowing what the process has requested the kernel to do. And then the kernel, looks at those arguments. The kernel knows what process was executing, so it can look at, process states such as what user is running this process, and that's the OS concept of a user. What permissions might be relevant? Is this process allowed to do what it just asked of me? And then it will decide if and how to fulfill that request. And then it'll do it and then return to the process and everything's happy, and your read or your write has just finished doing whatever it is, sending a cat picture out a serial port, if that's what you're doing. So Linux, being a very well-known operating system, has a pretty big and comprehensive syscall interface. There's about 313 different syscalls, I think, that ultimately provide the only mechanism by which a process can do anything interesting, anything outside of just churning around numbers inside its own happy little virtual memory land where nothing else exists. The syscalls are documented entirely in man2. You might get either the POSIX version or the Linux version, which are similar if not identical in behavior. And then kernel documentation also includes the ABI details, which is platform specific. And when I say that syscalls are the only mechanism by which a process can interact with anything outside of itself, you can do creative things with directly mapping memory into there, and maybe some special instructions that you're typically not allowed to execute without asking permission first from the kernel. Setting up shared memory can allow processes to communicate with each other without going through the kernel, but once again, you need to do some syscalls and talk to the kernel to set those up. So syscalls really do cover everything that a process can possibly do to interact with the world in a meaningful way. Weird side effect stuff like Spectre and Meltdown aside. So, examples of syscalls, I've kind of mentioned a couple of them. Your basic Unix file operations, open, read, write, close. Those are done by syscalls. A process that, once again, has no access to I/O, no concept of anything outside of itself, no real concept even of what is a file, has to request the kernel to open a file for it or request to read or write bytes. And typically the AT versions are used of these by glibc because reasons. glibc is complicated. But process lifecycle. Once again, a process can't do anything outside of itself, so how can it create another process or send a signal to another process? It has to do so by making syscalls to request the kernel to do that on its behalf. And then options that allow it to manipulate its own memory mapping. This is powerful and can be used to basically set yourself up in a situation where you can interact with the outside world without having to go through the kernel. So it's pretty interesting because managing the memory mapping unit or the virtual memory subsystem is a major part of what the kernel has to do to make sure that processes see their memory and only their memory. And mmap, or memory mapping and memory protect calls can give you a lot of fine-grained control over that and potential ways to work around assumptions and work around the way things are set up. And then, of course, there's some like famously convoluted and terrible ones. I/O control, the socket API is just an overloaded, bodged nightmare of a thing, and then about 300 more syscalls other than these. So the kernel provides a lot of facilities to a process that is running. And as I mentioned, there's a couple of non-syscall interfaces out there. There's like procfs or sysfs that let you basically do a lot of things that would previously done by ugly and horribly overloaded syscalls by just reading and writing to special files. But once again, read and write are syscalls themselves. And if you want to do direct I/O with just load and store instructions, you still need to go through an mmap syscall to set that up. So with all this said, there's a security concern. The syscall API is the kernel's attack surface from user space processes. This is not talking about sort of an I/O attack surface like where you can send the kernel something evil from outside that comes in over a wire and triggers bad behavior, but rather a misbehaving process can try to get the kernel to do bad things. And that attack surface explicitly is the syscall interface, the syscall API. There's also some concerns for defense in depth of just a user space, from just a user space perspective, preventing a process from doing anything unexpected. For example, your classic remote code execution that happens in a process is after a buffer overflow, you wind up executing some unplanned code or executing code in an unplanned way, eventually make an execute or an execve or an execute syscall of some sort to launch a new process or change the currently executing process and get a shell and do all the evil things. But once again, good luck doing that if that process isn't allowed to make that syscall. And that's where seccomp comes in as being a facility to implement sandboxing or to harden an otherwise implemented sandbox. For example, you could have a process open all of the files that it's ever going to need, and then just decide I'm done opening files. I'm going to give up access to that syscall. You could disallow the execution of any other processes. You know, if a program has started and it knows that in the course of normal operation it will never need to launch another program, it can once again give up that section of the kernel API because it knows that it won't ever need to do that. And if it ever does end up trying to do that, something has gone horribly wrong. Disallowing access to devices. Does something really need to be performing I/O? Or even just aggressively whitelisting something to only read and write. You know, if you've got sed or awk running as part of a pipe in a command thing, well, they really don't need to do anything other than read from standard input and write to standard output. Everything else they are just handling internally in their own little land. And that really continues. There's a lot of opportunity here to restrict that kernel API from that 313 some odd syscalls down to only what a process will be using. And that's what the seccomp facility provides. Seccomp is sort of the kernel feature that allows for syscalls to be turned on or turned off on a per process level by a non-privileged process. There are other kernel facilities, C groups, even like KVM for hypervisory stuff that can let you sort of put privilege boundaries into place, but all of those are either pretty heavily intrusive on what's going on or require root at some point to set them up. Seccomp is completely non-privileged. It has a very flexible and powerful way of expressing any sort of matching rules and the behavior that should be performed. So it doesn't just simply say whether or not something is allowed. You have options to go ahead and perform that syscall as normal, to return an eInval, just saying that it's an invalid syscall, or you can even send a signal to the process and basically have the process execute some other code instead to, for example, emulate the behavior it was expecting from that syscall without actually having to perform it. And this happens basically in a one-way transition. You make a seccomp call, and then you are done. Those rules now apply to that process for the rest of its lifetime and to spawned processes. There's a couple of calls that you have to call ahead of time, mostly just to disable a couple of options that you might have otherwise had to get around seccomp, and it won't let you enter seccomp mode without taking care of eliminating your ways out first. So seccomp in its most basic implementation was basically it was called seccomp set mode strict, and in strict mode, that's all you're allowed to do. You're allowed to call read, write, and exit. You have to have all of your files already open. You can read and write to them as much as you would like, and then you can exit when you're done, and nothing else is allowed, which is obviously inflexible, but also breaks everything under the sun. libc, for example, might end up making a sbreak syscall if it needs more memory. That's what the sbreak syscall does. It just gets you more memory, which if malloc doesn't have enough memory, it makes an sbreak call. Or not, it might do an mmap or something. glibc is weird. The at versions of syscalls, instead of a read, glibc uses read at, which is not allowed by seccomp mode strict. So there's a better mode. Seccomp mode filter is the cool one because it gives you flexibility, choosing which calls you want to filter, and potentially even looking at the arguments of those calls to decide whether or not to allow them. In addition to allow or deny, you can crash the process, you can return an error, you can send it a signal. The world is your oyster when you're writing seccomp filter rules. And there is some interesting applications of this. For example, I mentioned emulating I/O. There's two projects that I found. One of them is a bit of a niche project that's referenced in here that really does abuse ptrace as well to emulate expected behavior while still allowing a full sandbox to be constructed around an application without requiring root. But being able to even just signal into the process itself so that it can internally handle or replicate the behavior is interesting. Chromium actually was one of the first major projects to fully leverage seccomp to do interesting things. So, how do you write these seccomp filters and what makes them so powerful? They use a filter expression language, if you can call it that, called BPF, Berkeley Packet Filters, or BSD Packet Filters. And I know that says packet filters and we're talking about syscalls and allowing things based on their arguments. Just bear with me, it works out pretty well. So it was designed originally for matching on binary data that's contained in network packets. And classic BPF is an accumulator-based virtual machine. So, whoa, that's a touchscreen. So when you're writing these rules, rather than writing it as some sort of policy, it's actually written as a program. The virtual machine is very simple. It only has two registers, accumulator and index. It has some scratch memory that's read-write. And then it has read-only access to the memory or the data memory, which in the case of BPF and network applications is the packet itself. And one of the funniest notes on BPF was that during the SCO were rated, I can say fuckery because it's SCO. Yeah, during the SCO fuckery, one of the major points that they pointed to as proof that Linux stole code from them was the Linux implementation of BPF. SCO never owned BPF. Yeah. So it's just great. They can't even get it right. And the Linux BPF implementation was a clean room implementation based on BSD. Obviously, otherwise it wouldn't be around anymore. So BPF, as I mentioned, is implemented as a virtual machine that's capable of executing a filter program as a set of instructions. The instructions have a really simple encoding, 2 words per instruction. They're all fixed length. It consists of an opcode. There are 2 jump arguments, which are 8-bit unsigned jumps. You can't jump backwards. This helps with things like the halting problem. And K is a 32-bit constant that can also be encoded. The opcodes that you have are, for example, loading words, bytes or half words from the data, which is your packet data, into the accumulator, storing things to scratch memory to reference them later, and conditional jumps. And then, of course, all of the arithmetic that you would expect in an instruction set for a virtual machine. It has a couple of address modes, a non-exhaustive list. There's a very readable PDF that basically describes all of this from like 1992 when it was first introduced in BSD. You can encode a K, so for example, you can load or store an absolute value to later compare to. You can reference the index register itself. The accumulator is an accumulator, so it's implicitly always one of the operands. And then you can index into the data itself by either a constant offset or by the index plus the constant offset. So as an example, this program, and bonus points if you can figure out what it does, loads from 14 bytes into the packet, masks that off by ANDing it with a bit mask, shifts it to multiply by 4, moves that to the index register, and then uses that value to index into the packet further, loading a half word, and then jumping if it is equal to 80 to the condition. So those two jump values, it will jump the first one if the condition is true, it'll jump the second one if the condition is false. So it'll jump to the next instruction if it is equal to 80, and it'll jump to the ret 0 if it is not. That accepts HTTP packets. So, enough about packet filtering. Back to talking about seccomp and syscalls. BPF programs are what's used by seccomp to write policies. The implementation is really quite straightforward. The packet data is instead a struct seccomp data, and I have that struct definition on the next slide. We'll take a quick look at that. The BPF program has a couple of different return values it can return, telling it whether to allow, deny, return eval, send a signal, whatever. And you have all sorts of logic available at your disposal now, because you can, mask off certain bits, look at flags, sort of tease apart all of the flags and all of the arguments, determine whether or not you care about other arguments based on that. You have this whole virtual machine at your disposal to write that. But also at the same time, you have no ability to dereference pointers. This is actually by design, because it stops a bunch of race conditions that could otherwise happen. But crucially, that means that any argument that is a pointer, you can only write a policy based on where that pointer points, not the values that are at it. This is a bit overkill, maybe, for just filtering what syscalls should and shouldn't be available. But BPF has way more overkill in the kernel than this. There's even a whole committee's worth of patch sets about migrating everything to eBPF, which is just BPF on steroids. But we're not going to get into talking about that. Imagine writing scheduler policies in this same language. And you can compile Go to it already. So as I mentioned, the data that you're operating on is a struct seccomp data. You have the syscall number, and that basically is what syscall is being made. The architecture, which is just a magic value that tells you what architecture you're executing on, so you're comparing it to the right things. You have the instruction pointer, so you know where in the code it's trying to make the syscall from. And then you get to see the arguments to the syscall. And this is your data that you can then read from with your BPF program and decide whether or not to allow the syscall. They're pretty easy to implement, simple ones at least in C, handwritten. This looks like a lot, but it's really just an array of structs. Those structs are being assembled by macros with the opcode, and then those Ks and the trues and false. Note that the jump statement's the only one that has spots in the macros to encode the jump true and jump false jump distances. And basically this is just executed from the top down. Loads values into the accumulator, compares them, and then decides whether it should keep checking or return yes or no. And then eventually will return eperm if it's not allowed. So what are some of the applications for seccomp? I mentioned earlier that Chromium adopted it pretty early on. Chromium used it for attack surface reduction. As I mentioned when I was talking about syscalls and the syscall interface, the syscall API being the attack surface for the kernel. Kernel bugs exist. They're rare, but they exist. Well, I'm not even sure that calling them rare is fair, but they do exist. However, kernel bugs in implementations of syscalls that you can't access are no longer part of the attack surface. Chromium also, when Flash plugin was a thing, used a pretty aggressive seccomp policy to put the Flash player in naughty timeout land, which is just beautiful. Because Flash is so bad it doesn't even deserve access to all of the syscalls. It can be used to implement a sandbox without requiring root or C groups. There's some theoretical fun that can be had with this. We all know and either love or hate the way that mobile apps are quite well sandboxed from one another. They can't interact with other ones without, once again, going through a common API. If you imagine the Android API, you have to make special calls into the Android API if you want to access the network or draw on the screen or send a file to another app and perform these sort of high-level actions. That's possible in the case of Android because you're all running inside the Java virtual machine, and the Java virtual machine can enforce those rules. If you try to do something you're not allowed to do, it can just say no. Sort of like the kernel to a running process. Well, in this case, you could leverage seccomp into sort of disabling the kernel as the API, and now this application has to call into a different platform API, and now instead of writing an application targeting Linux, you can write an application targeting some sort of execution platform, and then the seccomp can be leveraged as a mechanism. This is applicable to things like Flatpak and Snap. They don't use seccomp, at least not integral to their architecture. I believe they do support it sort of as options, but that's potentially a way to build this sort of ecosystem or this sort of architecture on top of Linux. And that is not an entirely new concept. That is similar to how the VDSO in Linux works, which is just a little bit of magical kernel space that exists in every process and does useful things. And it's how some of the early 90s ugly bits of NT also worked. I'm not super familiar with the details, but it was pretty ugly. ROP and a lot of other modern exploitation techniques make this hazardous, but still definitely of at least academic interest. KMU also uses, or doesn't actually use, but KMU does have a mode where you can run it with seccomp mode, and once again, this is an attack surface reduction strategy. It just gets rid of the syscalls it knows it isn't going to use, reducing the risk of kernel bugs that could lead to like virtual machine breakout, which is obviously a bad thing. And containers also have the option of applying seccomp policies and going to magical Christmas land where everything is nice. But that's a talk for later. I have a couple of references on the back. As I said, Chromium has some interesting comments on it. There's a paper on implementing a full sandbox with it. I would actually be interested in picking up that sandbox that's several years old and seeing if there are any breakouts. Could be a fun way to experiment. And the paper on BPF is very much worth reading over. It's not particularly long and helps, especially seeing the massive growth in BPF in the kernel. And then there's official documentation on seccomp. So that wraps up my talk. I guess I'm free to talk about seccomp if anyone's super interested in it. Otherwise, yeah, thanks.